Every single day, we make calls on our phones without even thinking about it. But behind that simple tap of a screen is this incredible story of engineering genius, of engineers literally battling against the laws of physics. So today, we're going to pull back that curtain and see how it actually all works. Let's start with a number. 543. Back in 1976, that was the grand total of mobile phone customers in all of New York City. Think about that. In a city of 10 million people, only 543 could have a car phone. And there was a waiting list thousands long. The service? It was awful. Calls dropped all the time. So the real question is, how on earth did we get from that to a world where literally billions of us are connected wirelessly? Well, to make that jump, engineers had to solve a whole series of massive, what seemed like impossible problems. Okay, let's dive into this. So what was the big roadblock? What was holding everything back? It wasn't just about making a radio that could fit in your car. No, the real problem was figuring out how to give a clear, reliable call to millions of people, not just 5 or 4, 3, all moving around, all trying to share the same very limited airwaves. The first try was just a brute force approach. The idea was, let's just build one gigantic, super powerful antenna on the tallest building we can find and blast a signal across the entire city. And yeah, it kind of worked for a tiny handful of people. But it immediately created this massive bottleneck, a huge capacity crunch. With only a few radio channels to go around, the system was just instantly overwhelmed. Right, so the fundamental problem here is something called spectrum scarcity. The easiest way to think about it is like lanes on a highway. There are only so many radio frequencies available, and you just can't have two people driving in the exact same lane in the same spot at the same time. That one big antenna approach meant that once all the lanes were full, that's it. Nobody else could get on the highway. And then came the breakthrough, this absolutely ingenious solution from Bell Labs called the cellular concept. The thinking was, instead of one giant, high-power antenna for the whole city, why don't we break the city up into this honeycomb of smaller areas, or cells, and give each one its own little low-power tower? And this is where the magic happens. It's called frequency reuse. Because all those little towers are low power, their signals don't actually travel very far. And that means you can reuse the exact same radio channels in another cell just a few miles away, and they won't interfere with each other. All of a sudden, your 12-lane highway wasn't just 12 lanes long. It was 12 lanes you could use over and over and over again across the city. The capacity wasn't just doubled or tripled, it was multiplied exponentially. And the magic just gets better. Check this out. There's this amazing efficiency that comes from pooling these resources. The numbers here show that if you double your channels, say from 5 to 10, you can support more than triple the number of users. Double the channels again to 20, and the capacity just jumps like crazy. So a small increase in resources creates this massive, outsized increase in capacity. Okay, so we've solved the capacity problem. Awesome. But the cellular concept itself creates a brand new challenge. What happens when you're on a call, you're driving down the highway, and you leave one cell and enter another? If your call just drops, the whole system is basically useless. And that brings us to the next huge hurdle, the handoff. What the network does is this seamless digital relay race. As your phone's signal to its current tower gets weaker, the network is already scanning for the next tower that you're getting close to. The mobile switching center, which is kind of the brains of the whole operation, finds a free channel in that new cell, and then in a fraction of a second, it transfers your call. It happens so fast, you never ever notice the switch. So, and this is really the crucial point, a smooth handoff is absolutely vital. Think about it. There's almost nothing more frustrating than having a call drop right in the middle of a conversation. Engineers actually prioritize the success of a handoff above almost everything else, because if that fails, the whole user experience just falls apart. Okay, so we've got capacity, we've got mobility, but we're still fighting the laws of physics. In the real world, and especially in a city, radio signals don't just travel in a nice, clean, straight line from the tower to your phone. Oh no, they create this really messy, invisible problem called multipath.
Think of it like this. The main signal from the tower travels directly to you, sure, but it also bounces off that big office building. It reflects off that bus driving by. It scatters off the street. So your phone ends up getting the main signal plus dozens of these delayed echoes, these radio ghosts. And when these ghosts all arrive, they can interfere with the main signal, completely garbling it, causing it to fade and get all distorted.
So to fight these ghosts, engineers came up with two really clever tricks. The first is called diversity, which is basically like listening with two ears instead of one. By having two antennas, a phone can just pick the better of the two signals at any given millisecond, and that dramatically reduces the effect of all that fading. The second trick is equalization, which is like digital noise cancellation but for echoes. A smart chip in the phone analyzes the distortion and creates an inverse signal to cancel the echoes out, cleaning up the original sound. Pretty cool. So even with the whole cellular concept, the demand for service was just exploding. The original analog systems were hitting their limit. So the next great challenge became one of pure efficiency. How do we squeeze even more conversations into that same tiny sliver of airwaves? And the answer was to go digital. See, the old analog method, FDMA, it was like giving every single caller their own private radio station. It worked, but man, was it wasteful. The new digital methods were so much smarter. TDMA sliced up each channel into tiny time slots, letting multiple users just take turns, like people in a really fast, perfectly timed conversation. And then CDMA. It gave each user a unique digital code, letting them all talk at the same time on the same channel, like a bunch of different conversations happening in the same room, but all in different languages. This digital leap, this was the final key. By encoding information on radio waves in a much smarter ways, using these really sophisticated techniques like the ones you see here, engineers could unlock just huge gains in capacity. And that meant better call quality, way better performance against those radio ghosts, and it paved the way not just for more voice calls, but for the mobile data that basically defines our entire world now. This digital shift created the wireless era we're living in today. So when you think about it, we went from just 543 users in one city to a globally connected society. The story of the cell phone is a story of human ingenuity, just solving one impossible problem after another. We solved the great challenges of the 20th century. But now, as we're looking to a future with self-driving cars, smart cities, trillions of connected devices, a whole new set of impossible problems is waiting. The challenge for sure continues.